So now we're actually, within our system, we're going to be talking about phase changes. And we talked, you guys are fine with whole solid melting to form a liquid, and liquid going ahead and forming a gas. Those are phase changes. And there's energy associated with those phase changes. Okay, so in general, it almost seems like it should be like a rap song, or, okay, it's kind of catchy. But when I talked about a solid going to a liquid or a liquid going to a gas, what we're doing in those cases, you know you have to heat it, right? You have to heat an ice cube to make it liquefy. You have to heat water to go ahead and make it vaporize. And actually, when you heat it, you are breaking those bonds between the water molecules. So that it takes energy. Maybe less intuitive, and we'll be talking more about, let's see, instead of evaporating or vaporizing, condensation, okay, when something goes from a gas to a liquid, and instead of melting, we're going to be talking about freezing or solidification, when something goes from a liquid to a solid. In that case, bonds are formed and energy is released. So that's a little less intuitive. Okay, so I could animate this, but I'm not going to. That's one of the things when I think about matter, if matter's in its gaseous stage, and I have a table coming up here in a minute to show you, it has the most kinetic energy, okay, and basically it can fill the container it's in, so its volume is infinite and its shape is indefinite, okay. Compare gas to a solid, and solid has the least amount of kinetic energy. It has a high degree of intermolecular bonding. Okay, so when we talk about it takes energy to break bonds, okay, we could be talking about those bonds between ions, those bonds between ions and molecules, and those bonds between molecules and molecules. Okay, so it takes energy to break bonds. So at the top there, you see the three physical phases of matter that we're concerned about: solid, liquid, and gas. So kind of from left to right, we're breaking bonds. We've been talking about endothermic processes. Okay, so endothermic, endo meaning putting energy in. If we were to put a Q or a delta H, that would be what? Positive, right? Does that make sense? Greater than 0? All right. So from right back to left, if a gas goes to a liquid or a liquid goes to a solid, energy, I said, is going to be released. Bonds are being formed, and actually the Q, the change in thermal energy, or the delta H associated with these phase changes would be negative. Does that make sense? We're going to kind of be hitting that. So actually, here in a minute, I'm going to have a delta H's, and these are going to be negative, and these delta H's are going to be positive. Okay? Endothermic, exothermic. So whenever I think the next slide is, okay. So again, the solid, liquid, gas across the top there. And if you go from left to right, the solid ultimately to gas, I think of as adding heat to get from solid to a gas. Okay. Actually, your little particles are going to be going faster. Your particles will have higher kinetic energy. That's why this is over here, okay, associated with higher kinetic energy. If you're going from right back to left again, okay, a gas to a liquid or a liquid to a solid, energy is released. Your material will have lower kinetic energy. So this is actually a table that we had clear back in Unit 1. Where over here on the right we have your different phases of matter, and we can talk about them in terms of kinetic energy, like we just said. Gas has high kinetic energy, solid has a low kinetic energy. Okay, and then actually in terms of bonds between the particles, and we'll be talking about this in Unit 5 in here, if your physical phase of your matter is gas, then actually we assume there are no intermolecular bonds. It's if it's behaving ideally. If it's a solid, a lot of intermolecular bonds. So from solid to a gas, energy is required. E required, i.e. endothermic, endo, okay. And so, of course, when it goes from a gas to a liquid to a solid, energy is released. In meteorology, we talk a lot about clouds, and what a cloud is basically it's nice and milky white because water is in its liquid state. And honestly, a fair bit of energy is released when in the atmosphere water condenses. Okay. So just to make sure we're all on the same playing field, underneath those transitions, I'm going to go ahead and put numbers, or excuse me, put verbs or whatever you call those. I don't know. I'm not an English person. If something goes from a solid to a liquid, we call that melting. If something goes from a liquid to a gas, we call that evaporation or vaporization. Same thing. From a liquid to a solid, we call that freezing. From a gas to a liquid, we call that condensation. So these are all kind of important changes in which energy is released or energy is required. And here, when we work a problem, there's only one problem to work as part of this lecture part. We're going to be looking at these energies. I think there's audio here. But this should play. And not burst an eardrum. Or not. Oh, I know. Somehow my default player is doing that silly, it doesn't like that. Always something. This should work. Quick time. One more try. Open with. Yeah. Don't share it. 1001, 1002. Ah, that's looking promising. Come back here. All right. Ah, I have my mute on. Got that. All right. Down here. I was trying to be quiet.
Molecules of a liquid have a range of kinetic energies. Some have enough energy to overcome intermolecular forces. If these high-energy molecules are at the surface of the liquid, they can escape into the gas phase. This is an endothermic process.
Okay, so it takes a little bit of energy for each one of those cute little liquids to go from its liquid state into its gaseous state. And where does it get its energy? It gets its energy from the warmth of the solution. Or if there's a Bunsen burner down there warming the solution. Okay. I thought you had your hand raised up and it was your hat. Yeah, I've got a few movies, so we'll see if this one goes any smoother. So there is, and some of you guys already know about this, there is this important sort of phase change in which something skips the liquid stage basically. And we call that in general sublimation. So actually you can say sublimation has occurred if a solid goes to a gas, directly to a gas, right, skipping the liquid stage, or something goes from a gas directly to a solid, skipping the liquid stage. It's called sublimation. And it happens all the time. Like, for instance, we have a frost warning out, like tonight, maybe. So the deal there is you might, in the morning, see solid frost on your cute little blades of grass. Odds are that it did not go through the liquid stage. Okay? It basically came out of the atmosphere from a gas right to a solid. Okay? I prefer actually the word deposition for that, but that's okay. You can use sublimation or deposition. And we said when something goes from a gas to a liquid or from a liquid to a solid, we said energy is released. So honestly, if you were to, and sometimes farmers may take advantage of the formation of frost, just a little bit of energy is released when frost forms. You're like, really? Yeah. Okay. So this, we'll see if this works for you. Oh, another one is like, you guys are so spoiled. I bet everybody like has a freezer with an ice maker. But before you had ice makers, you had to use like trays, put water in them. Okay, and there is a chance that if you wanted ice cubes, you're like, hey, I need ice cubes. I better put some water in my trays. So if you forget them in your freezer for a while, but you go back and you're like, 2 weeks later, you're like, okay, I'm ready for my ice cubes. Well, there's a chance that it will have solidified and then it will have sublimed within your freezer. So basically it went from being a solid, which is what you wanted, to going ahead to being gas in your freezer. Okay, sublimation. Another, I think, important time for sublimation is around here when we have these snowfalls and we get these big piles of snow in our parking lots. Well, if the temperature is cold enough, that stuff is, it might settle a little bit, but it's not going to melt. But don't you see sometimes where that solid starts to go away? Okay, it's subliming. Another very important thing, especially this time of year, Halloween, is dry ice. What is dry ice? Dry ice is carbon dioxide they pressurized it and cooled it. So basically, carbon dioxide is a solid. Well, if you go ahead and take it out of your ice chest carefully, right? Dry ice can get nasty burns. It goes directly from being a solid to being a gas. So, I wonder if this one is going to open in the wrong player.
In the flask is solid iodine. In the test tube is ice.
No, it's not. Silly. I think it's an easy fix. I'll just fix it here. I think all you got to do is properties, open with, change, time. All right.
I think you have to hit apply.
Oh, I think I should have, but I didn't.
In the flask is solid iodine. In the test tube is ice. When we heat the iodine, its weak induced dipole forces are overcome, and the iodine sublimes into the gas phase. The gas recondenses as a crystalline solid on the cold test tube.
That purple haze there is I2 in its gaseous state. And it skips the liquid state just because of how it wants to be a solid or a gas, but not a liquid. So, all right. Okay, so endothermic energy put in. And we said endothermic processes have positive Q's, okay, and they have positive delta H's. So common everyday phase changes of melting and evaporation or vaporization. And sublimation, if something like dry ice is going from a solid to a gas, those will all require energy. It's kind of neat. If you think about it, they require energy. So for instance, if your hand is in the vicinity of any of this, doesn't your hand get cold, possibly? Your hand provides the energy. So kind of then looking back the other direction where bonds are being formed, when something goes from a liquid to a solid, we call that freezing. When something goes from a gas to a liquid, we call that condensation. Bonds are being formed. We know, as instance with frost, that something can go from a gas straight to a solid. Okay, those are exothermic phase changes. So energy actually is released. And I always, like I told you, think of condensation with regard to weather and clouds. Condensation, clouds are warm and toasty, actually, to a certain extent. So all of those heats, all of those energies released, or all of those energies absorbed or taken in by something phasing, going through a phase change, those are all called latent heats. Latent heats. They cover all of those energies associated with phase changes, whether that's exothermic or endothermic phase changes. Latent heat. Okie dokie. So, there are tables out there with heats of vaporization. Heats of vaporization. Okay, enthalpy of vaporization, heats of vaporization for all sorts of things. The thing is, it'll either be given in terms of energy per gram or energy per mole of that substance. So vaporization and condensation are linked by the same things changing phase, but one is going kind of from left to right and one is going from right to left. Okay, so vaporization and condensation, they both involve gas and liquid. Vaporization, you're putting energy in. Condensation is energies coming out. Okay, they both involve the gas-liquid physical phases. So I'm going to tell you the catch here, though. This isn't the catch. But if you're breaking bonds in vaporization, remember vaporization is evaporation. It's the same thing. If you're breaking bonds in vaporization and you're forming bonds in condensation, it's the same amount of energy. If you're familiar with the absolute, value signs, that's what those are. But as we have kind of done with regard to how we flipped reaction, okay? We flipped our products on our reactants, and we had the same magnitude of the enthalpy of reaction, but opposite in sign. And that's what we have here. Okay? So here's the deal. I always get this mixed up. You are going to see, and I think I have it coming up, for water, for instance, you will have a table that says the heat of vaporization, the latent heat of vaporization, the delta H vap, but you won't for condensation. So you'll just have to pick that number and add a negative sign to it. Okay. So you will not find tables for latent heats that basically are exothermic, only the endothermic ones. So you'll find the heats of vaporization, and if you need the heat of condensation, and we're going to, so I'm trying to think. I know on your homework you're going to have to do this. All right. So let's look at the other pair. Now, you would think melting would be a better term, and I do not know why we actually use fusion instead of melting, but it's the same thing. Okay? Notice what heat of fusion is it's melting solid to a liquid. Okay, so that's one of the things you're going to want to get into your brain. And that, again, is endothermic. Got to put energy in to melt stuff, break those bonds. Okay, so the heat of fusion is equal to the heat of melting. Positive delta H, okay. So the opposite of melting would be freezing. Okay, so The heat of fusion and the heat of freezing have that same relationship. The heat of condensation and the heat of vaporization have. Okay, they both involve the solid-liquid phase change. So they're equal in magnitude but opposite in sign. So like I said, tables usually will have the endothermic, where bonds are being broken, but where they won't have the exothermic, where bonds are being formed. So bonds are being broken with the fusion or the melting. So heats of fusion is what you're going to see on a table. Okay. So speaking of a table, and I'll show you why. Of course, do you guys know MP stands for melting point temperature? Sometimes and the example we're going to do with water, you're going to need to know the melting point temperature and the boiling point temperature. So this is melting point. Do you buy this, that it's also freezing point? Yeah, okay. Freezing and melting point. It's the temperature, right? It's the transition temperature. Okay, so there's the energy that would be required per gram and energy that would be required per mole of those of these metals. And if you're thinking, hey, I know how to go back and forth between grams and moles, and so you actually could confirm this if you wanted to. They're the same numbers. And which one you use depends upon what amount you're given in terms of, are you given it in terms of grams or moles? So for those same substances, we have the warmer part. Okay, so BP stands for, yes, boiling point temperatures. Temperature at which they will phase change from a liquid to a gas, and also condensation temperature too, right? So down there then are for compounds. Matt, sit up at least, okay? Thanks. All right. Very good. If you're like me, you kind of look at tables, you're like, well, what looks interesting? Well, you know, this looks interesting. You know, the boiling point temperature of methane is negative 161 Celsius. So it boils at that temperature. And we're about 30 degrees Celsius right now. So guess what? It is a gas right now. That's all that's saying. Okay, that makes sense? Okay, so now on to the problem. And we are going to, remember that change in enthalpies, or delta H's and Q's, change in energy, they are independent of their state function, which means they are independent of path. So we are actually going to kind of create some stepwise functions here as we talk about a very cold piece of ice. Okay, notice that this ice is below the freezing point temperature. It's like negative 50. We're going to take that little piece of ice, and we're going to talk about what energy do we need to put in to ultimately take that mass all the way up to a temperature that's above its boiling point temperature. So I'm hoping you're thinking water, you're thinking maybe it freezes at 0 Celsius and it boils at 100 degrees Celsius. You're right. So we're going to kind of think of this stepwise, and changes in thermal energy. And there's 5 steps. And so like what I tried to say is these steps don't have to occur all of this step and then all the next step and all the next step. But they ultimately, overall, need to occur. So the fact that that chunk of ice is cooler than freezing means our first task is to go ahead and get it to the freezing point temperature. And we're going to do that using Q is equal to M C sub P delta T. I'll go ahead and, I'm going to do this later, but I'll go ahead and Q of the ice change of thermal energy of that really cold piece of ice is equal to the mass of the ice times the specific heat of the ice times the change in temperature of the ice. Now we're just going to take it from -50 to 0. So then we're going to say, all right, so we warmed up that ice right to 0 degrees Celsius. Now what we're going to do is melt it. And by golly, to melt it, we are going to take the mass, and then coming up with the Q required to melt is really pretty easy. We're just going to take the mass, which is that 50 grams, and we're going to multiply it by the heat of fusion. That's it. Okay, so that's going to be our second step. And then it's going to be a liquid, right? And then what we got to do, step number 3, is once it's a liquid, we're going to say, all right, I want to take it from 0, from the temperature it liquefied to the temperature it's going to vaporize. So we're going to leave it a liquid, and we're going to go ahead and we're going to use Q is equal to MC sub P delta T there. Q of the water liquid is equal to the mass of the liquid, and the mass is going to be the same all throughout here. But the specific heat of ice is different than liquid water, delta T. And in this case, our delta T is basically going to be 100 degrees. Okay, so we're going to add up all of these Q's. But can you see where actually, and this didn't hit me till just now, we've been talking about, oh, the change in thermal energy of the system is 0. The change in thermal energy of the system is 0. But honestly, the change in thermal energy of this system is not 0. We're going to have to have some sort of a Bunsen burner under there and be pumping energy into, go ahead and get that chunk of ice that's -50 up to 200 degrees Celsius. Okay, so Q of the system is not 0. So then once we have it all up to the boiling point temperature, 100 degrees Celsius, then we're going to need to vaporize it. And then we're going to use what we've been talking about just this afternoon. The Q of vaporization, we're going to take the mass of the water, I'll go ahead and put mass of liquid, it's the same, times the heat of vaporization. What does that say? I try to read my own, the Q associated with vaporization, I guess. Okay, good. All right. So then at that, if you're keeping track, now we have a gas at 0 degrees Celsius. And 100 degrees Celsius. We have a gas at 100 degrees Celsius. And the last thing we need to do is jack that gas from 100 degrees Celsius to 200 degrees Celsius. And here we're going to go back to what we learned earlier, the change in thermal energy of the gas, or the vapor, either one, is equal to the mass of the gas, oh, that rhymes, okay, times the specific heat of gas, which is different as it's a solid or a liquid for water, okay, times the change in temperature of the gas, which we're picking up at 100 degrees Celsius and ramping it up to 200. Okay, so it's a story of lovely ladies. I could not resist. Okay, so honestly, yeah. The change in thermal energy of our system is not 0. We are pumping it past the boundary. If it's in a beaker, we're definitely have some energy coming in. The change in thermal energy associated with all of this, okay, added together then, will be equal to our Q of interest. So as we've been talking, and I think I have builds here, I'll kind of show that kind of from left to right we are pumping in energy. This is the amount of energy we're pumping in. It can be time or actually energy, adding energy at kind of a constant rate, I guess. And then here is what the temperature is. So the first step we talked about, okay, was where it is actually, we are taking the ice from -50 to 0. Okay, that's this right here. Okay, so we pump in a certain amount of energy and it raises your temperature of your solid. Then we pump in a certain amount of energy and it doesn't change the temperature of your solid, it just melts it. Okay, so this plateau right here is melted. Then we go ahead and add energy to your liquid now, and we jack up the temperature from 0 degrees Celsius to 100 degrees Celsius. Okay, so that's raising the temperature of the liquid. And these are our 5 Qs. Once it's a liquid, then we go ahead, that long plateau right there is the amount of energy you need to pump into it in order to get it to go from a liquid to a gas. That's a lot of energy, right? And then the last little bit is once it's a gas, you got to take it from 100 degrees Celsius up to 200. Okay, so that's kind of what we have going on. There are 5 there. 1, 2, 3, 4, 5. So that's the strategy, and here's the execution. So the first is to take that very cold piece of solid ice from -50 to 0. And doing that, we use that good old change in thermal energy is equal to mass times the specific heat times the change in temperature. So plugging them in then, it should look like this. And you're going to see me go ahead and introduce this energy term to get them from joules to kilojoules, just because I prefer that. It's neater to me. So our first Q is 51.5 kilojoules, first of 5.
Did you originally have this problem with Kelvin?
No.
That's what it has.
Does it?
J,
Or Kelvin?
G, K, so I just assumed it was Kelvin.
Oh. That's interesting. I must have. I must have. I didn't realize it. So what she's saying is, you know, the thing about it is they're both the same unit. So what I'd probably do if I was working this problem would be more descriptive than the subscript 1. I would say Q of warming ice or something that makes me remember it, you know, something more descriptive than 1. Okay. So now we are at 0 degrees Celsius, and we are ready to go ahead and melt that stuff. So, like I said, you're going to remember the heats of fusion are given per mole or per gram, and so we'll go with the per gram one, right? So if you look back for water, it's 333 joules of energy per gram that it's going to melt. So this one's not too bad. And again, being more descriptive, instead of 2, I would probably put melting. These are all going to be positive, right? Because we're putting energy in this. And then once it's all a liquid, then now we're ready to go from the melting point temperature to the boiling point temperature. Okay? So now, and that's why the temperatures are so important, those two temperatures on that table. So our delta T is going to be 100.0 degrees Celsius. We're back, since it's a liquid, to using that familiar specific heat of 4.184 joules per gram degree Celsius. Okay, so the amount of energy to raise the temperature of that 500 grams of liquid now from 0 to 100 is 209 kilojoules of energy. So something more descriptive, I might say Q of warming water. Warming liquid, I guess it would be. It's funny how if somebody says water, they assume it's like liquid, but it doesn't have to be. Okay, so once we're up to the boiling point temperature with our liquid, we're ready to evaporate it. So we're going to use the heat of vaporization. So the heat of vaporization for water is, have to pump in 2.26 times 10 to the third joules per gram that you want to evaporate. Okay, so sticking in our mass of 500 grams, using that latent heat of vaporization, and taking it all the way to kilojoules. This is our fourth term. So Q of vaporization. And we're almost done. So once it's all a gas now, remember the final temperature wasn't 100, the final temperature was 200. Okay, so we're going to use that Q is equal to MC sub P delta T for that last leg. And don't forget the specific heat of water as a solid, liquid, and gas are different. The only specific heat I need you to commit to memory is the specific heat for liquid water. But when water is a gas, the specific heat is 2.03 joules per gram degree Celsius. And again, you see where it's always, delta T's are always final minus initial, so these have all been positive delta T's. The final temperature of 200 from the boiling point temperature of 100. So to be more descriptive, instead of 5, I would probably put, what, heat, gas or something? Some vapor. So that's the fifth leg. So then if we add all these together, here they are, Q1 through 5. So remember, since we're adding together, we go with the fewest number of decimals, which would be actually in the ones place. Oh, no, it's not, sorry. Fewest number of decimals, which is in the tens place. It's like, oh, it's in the tens place. Honestly, when it gets down to this step, I'm not as picky about rounding as I am with some other sort of things. So that's the answer. Like, alrighty then. Okay. So again, this is the 1 through 5. And oops, let me go back. Are there any questions other than how do you do that?
I have one.
Yeah.
On your step 3, when you did the temperature change, you did 100 minus 0. Is 0, is that just the freezing point?
Yes, that is because of the freezing point. Very good. Yep. Did everybody catch that? And this is just because water, the boiling point is 100 degrees Celsius, and the freezing point is 0 degrees Celsius. Yep. Okay, so now I diagrammed the first three. I didn't get to the last one. But I will. Maybe I'll push these first three out there in case you're, and then you can always text me. So let's take a look at what you have available to you. You leaving? Okay, bye. So this one, if you read it a few times, it's just saying there's two things going on, and it basically, because I started to say they were in the same container, this ice and this water, but they're not. It basically says what mass of ice can be melted. I'm going to put it over here on this side of the squiggly line. What mass of ice can be melted with the same quantity of heat that is required over here. And then it goes ahead, describes a number of moles of water. It gives the delta T of the water. And of course, the change in thermal energy of the water is Q is equal to mc sub P delta T. So we can get the mass from the moles. Okay, so we can come up with the change in thermal energy of the water. Then if you go on to work the problem then, okay, there's my little ice cubes. It says now the amount of energy needed to melt ice is 6.01 kilojoules per mole. That's the heat of fusion, right? And we've been talking today how the energy required for fusion, we can either take the moles or the grams, the mass of the moles, times the heat of fusion to get the energy required. And then in this particular problem, like it says, assume that this heat of fusion is equal to the energy associated with heating up that water. So basically, you know this, and you know this, of course, because you looked it up, and you're supposed to come up with the mass of water. You can knock out the moles of water like that, and then you have to convert moles to grams. The next one, it's kind of a fun one. We have a phase change. It says you're going to go ahead and pump steam into a certain amount of water. It gives you the mass of the steam. Okay? And notice it gives you the temperature of the steam is kind of fun because it's right at the phase change of water. Okay? So it's right at the boiling point temperature of water, 100 degrees Celsius. And you're going to go ahead and admit that to a certain amount of water. Your water in here is liquid, and right away your steam is going to go ahead and condense. We said during condensation, energy is released. And notice that the heat of condensation isn't given, but the heat of vaporization is given. So we said you can get the heat of condensation from vaporization. It's the same number, but opposite in sign. So that's the amount of energy that's going to be released. It gives the mass of the water you're bubbling that steam into is 100.0 grams. It gives the initial temperature of the water, 25 degrees Celsius. So here's part of the problem with this problem. Your water is going to heat up, and your steam is actually going to cool down from its initial temperature of 100. So we actually end up with three terms. So I was trying to describe what this is, and I probably could have done maybe a little better, but here's our three terms. We have a heat associated with the condensation of that 5 grams. And like I said, we have a heat associated with that gas cooling down from 100 to some final temperature. And then I went ahead and said the final temperature of both of these things, the gas and the water, that final temperature is going to be the same common temperature like we've talked about before. That T sub F is the same. So it's a little messy, and I kind of remember working this. This actually is a situation in which the change in thermal energy of the overall system is equal to 0 because we're assuming that the steam is admitted, it's part of the system. So that's my hints. It's challenging. Take a look at it. The last one that I had time for is basically you're dropping these stainless steel balls into some water. The initial temperature of the stainless steel balls is given. The specific heat of the stainless ball is whatever stainless steel is. Specific heat is given. The volume of the water you're dumping it into is given. Of course, we can get to the mass of the water using density. The initial temperature of the water is given. That's 28.5 degrees Celsius. And the specific heat of water you already knew. So here's the deal. If you read it a few times, it says that it already tells you that this stainless steel is so hot, and that's quite a bit of mass. It's going to boil your water. So right away you know that the final temperature for them both is going to be 100 degrees Celsius. So the water, you know delta T's. You know that the water is going to warm up to 100 from 28.5, and actually your hot shot is going to cool down from 225 to 100. So the final temperature of both of them is the boiling point temperature of water. So the things you have going on there, then, there's three things. You have your stainless steel. There's a certain amount of change in thermal energy. Okay, you have the mass of the stainless steel, the specific heat of the stainless steel, the change in temperature of the stainless steel. You have your water undergoing a change in thermal energy. And then you have evaporation occurring. And actually, that's what you're after. What mass of water will vaporize? So the Q of vaporization is equal to grams or moles times the heat of vaporization. And of course, you know heat of vaporization. You know all this stuff, and it's equal to 0. So you actually can solve for the moles or grams. Okay? Yeah. So I'll try to get the 32 up. But like I said, I might push these out there. Give me a little more time.
Do you have our lab calculations up?
Yes. From yesterday?
Yeah.
I think so. Let me know if I don't, but I think I do.
Okay.